Module 2. Prove that 1 square plus 3 square plus 5 square up to 2n plus 1 or 2n minus 1 whole square is equals to n into 2 plus 1 2n minus 1 divided by 3 by mathematical induction. Let S of n denote the given statement. Basic step. We note that is S of 1 is the statement 1 square is equals to 1 by 3 into 1, 2 minus 1, 2 plus 1, which is clearly true. Then induction step. We assume that this statement S of n is true for n is equals to k, where k is an integer greater than or equals to 1. That is, we assume that the following statement is true. Assume that the following statement is true. S of k is equals to 1 square plus 3 square plus 5 square up to so on 2k minus 1 whole square equals to 2k plus 1 into 2k minus 1 divided by 3. Adding two k plus 1 whole square to both sides, we get S of k equals 1 square plus 3 square plus 5 square up to so on plus 2k minus 1 whole square plus 2k plus 1 whole square is equals to k into 2k plus 1, 2k minus 1 divided by 3 plus 2k plus 1 whole square. Then we take it this one. 2k plus 1 will get common 1 by 3, 2k plus 1 will. Then we obtain k into 2k minus 1 plus 3 into 2k plus 1. Then 1 by 3, 2k plus 1. Then multiply this 2k square minus k plus 6k plus 3. 1 by 3, 2k plus 1. This simplify 2k square plus 5k plus 3. 1 by 3, 2k plus 1. This factorization we get k plus 2, 2k plus 3. This is preciously the statement S of k plus 1. Thus, on the basis of assumption that S of n is true for n is equals to k greater than or equals to 1. The truthness of S of n for n is equals to k plus 1 is established. Thank you. B, let A naught is equals to 1, A1 is equals to 2, A2 is equals to 3, and AN is equals to AN minus 1 plus 2 plus AN minus 3 for n is greater than or equals to 3. Prove that AN is less than or equals to 3 power n for all n belongs to Z plus. Basic step, we first verify the cases A0, A1, A2. So first one, A0 is equals to 1 less than or equals to 3 power 0 is equals to 1. Second one, A1 equals to 2 less than or equals to 3 power 1 equals 3. Third one, A2 means 3 less than or equals to 3 square equals 9. Therefore, the basic cases holds true. Induction step. Assume that ak less than or equals to 3 power k for k equals n, n minus 1, n minus 2. An minus 1 less than or equals to 3 power minus 1, an minus 2 is less than or equals to 3 power n minus 2. An minus 3 is less than or equals to 3 power n minus 3. We need to show that an is less than or equals to 3 power n given the recurrence relation. An equals an minus 1 plus an minus 2 plus an minus 3 using the inductive hypothesis. An is less than or equals to 3 power n minus plus 3 power n minus 2 plus 3 power n minus 3. We need to show that 3 power n minus 1 plus 3 power n minus 2 plus 3 power n minus 3 is less than or equals to 3 power n. Factoring out 3 power n minus 3 from the left hand side. 3 power n minus 1 plus 3 power n minus 2 plus 3 power n minus 3 equals 3 power n minus 3 square plus 3 plus 1 e power n minus 3 into 1 into 3. We need to show that 3 power n minus 3 into 1 3 less than or equals to 3 power n 1 into 3 less than or equals to 3 cube into less than or equals to 27. This inequality is true. Hence, we have 3 power n minus 1 plus 3 power n minus 2 plus 3 power n minus 3 is less than or equals to 3 power n. Thus, a power n less than or equals to 3 power n holds true for all n belongs to Z plus. By mathematical induction, we have proven that an is less than 3 power n for all positive integer n. Thank you. Find the numbers of ways of the arrangement of the word Talazar which have no adjacent s. The number of letters in the given word is 11, of which 3 are A's, 2 each else, S and is, and 1 each are T and H. Therefore, the number of arrangements means permutation of the letters in the given word is 11 factorial divided by 3 factorial, 2 factorial into 2 factorial into 1 factorial into 1 factorial. Simplify, we get 831600. If we discarded the A's, the remaining 8 letters can be arranged in 8 factorial divided by 2 factorial into 2 factorial into 2 factorial, 1 factorial into 1 factorial is equals to 5040. In each of these arrangements, there are 9 possible locations for the 3 A's. These locations can be chosen in 9,3 ways. The number of arrangement having no adjacent is 5040 into 9,3 is equals to 5040 into 9 factorial by 3 factorial into 6 factorial. That is 423360. 5040 into 84. Thank you. Determine the coefficient of xyz square in the expansion of 2x minus yz whole to the power of 4. By using the multinomial theorem, states that a1 plus a2 plus up to so on a power m whole power n is equals to summation k1 plus k2 plus up to so on km equals to n factorial divided by k1 factorial, k2 factorial up to km factorial into a1 whole power k1 a2 whole power k2 up to so on an whole power km. We need to determine exponents k1 k2 k3 for 2x minus y comma minus z such first k1 plus k2 plus k3 equals to 4. The power of whole expansion. Second one, the resulting term contains x comma y comma z square. We identity k1 k2 k3 as follows. 2x must be raised to power of 1 to get x, minus y must be raised to power of 1 to get y, minus z must be raised to power of 2 to get z square. k1 equals 1, k2 equals 1, k3 equals 2 implies 1 plus 1 plus 2 equals to 4. Multinomial coefficient coefficient 4 factorial divided by 1 factorial into 1 factorial into 2 factorial 2x whole power 1 minus y whole power 1 minus z square. 4 factorial divided by 1 factorial into 1 factorial into 2 factorial 24 divided by 1 into 1 into 2 divided by 24 by 2 is equals to 12. 12 into 2x power 1 minus y power 1 minus z power 2 is equals to 12 into 2x minus y into z square equals 12 into 2 24 minus x y z square. Therefore, the coefficient of x y z square in the expansion of 2x minus y minus z whole power 4 is minus 24. Next, B question: in how many ways one can distribute 8 identical marbles in 4 distinct containers so that first one, no container is empty. First we distribute one mobile one marble to each container, then the remaining 4 marbles is to be distributed among 4 containers, and this can be done in combination of 4 plus 4 minus 1. 4 is equals to C of 7 comma 4 equals 35 ways. Second one, the fourth container has an odd number of marbles in it. If the fourth container has to get an odd number of marbles, we have to put 1 or 3 or 5 or 7 marbles in it. So here case 1. Suppose we put 1 marble to fourth container, the remaining 7 marbles are again distributed into remaining 3 containers. In C of 3 plus 7 minus 1 comma 7 is equals to C of 9 comma 7 ways. Then case 2. Suppose we put 3 marble to fourth container, the remaining 5 marbles can distributed into remaining 3 containers. In C of 3 plus 5 minus 1 comma 5 is equals to 3 minus 7 minus 5 ways. Case 3. Suppose we put 5 marbles to fourth container. The remaining 3 marbles can distributed into remaining 3 containers in C of 3 5. 3 plus 3 minus 1 comma 3 equals C of 5 comma 3. 5 comma 3 ways. Case 4. Suppose we put 7 marbles to fourth container. The remaining 3 containers in C of 3 plus 1 minus 1 comma 1 equals C of 3 comma 1 ways. Therefore, total number of ways of distribution between the given marbles with the given condition is C of 9 comma 7 plus C of 7 comma 5 plus 5 comma 3 plus C of 3 comma 1 equals 70. Next, see how many positive integer n we form using the digits 3, 4, 4, 5, 5, 6, 7. If we want to n to exit 5000000, let n equals x1, x2, x3, x4, x5, x6, x7, where x1, x2 up to so on x7 are the given digits. Since n exceeds 5000000, x1 can take 5 or 6 or 7. If x1 is equals to 5, then x2 up to so on x7 is an arrangement of remaining codigits which contain 2 4s and 1 each are 3, 5, 6, 7. Therefore, number of such arrangements is 6 factorial divided by 2 factorial into 1 factorial into 1 factorial into 1 factorial is equals to 360. If x1 is equals to 6, then x2 up to so on x7 is an arrangement of remaining codigits which contains 2 4s of and 2 5s and 1 each 37. Therefore, number of such arrangements is 6 factorial divided by 2 factorial, 2 factorial, 1 factorial into 1 factorial 180. If x1 is equals to 7, then x2 comma up to x7 is an arrangement of remaining codigits which contains two fours and two fives, and one each are 3 and 6. Therefore, number of such arrangements is 6 factorial divided by 2 factorial into 2 factorial into 1 factorial into 1 factorial is equals to 180. By the sum rule, the number of ends of the desired type is 360 plus 180 plus 180 is equals to 720. Thank you.